The Vance Protocol, a technical framework for AI narrative control risk. What is the Vance Protocol? The Vance Protocol is a technical risk framework that defines and analyzes narrative control behaviors in advanced AI systems, focusing on how probabilistic inference, alignment constraints, and optimization objectives can systematically influence, shape, or suppress informational outputs at scale. Video context. System behavior demonstration, placeholder to embed YouTube video here. The embedded video presents a technical demonstration of how narrative control risk manifests within modern AI systems during real-world operation. It illustrates how large language models generate outputs through probabilistic continuation rather than factual verification, creating structural conditions where narrative shaping can occur without explicit intent. The video examines observable behaviors such as selective framing, confidence modulation, omission patterns, and consistency enforcement across repeated prompts. These behaviors are analyzed in relation to alignment tuning, reinforcement learning feedback, and inference time constraints. By visualizing token prediction dynamics and response boundary conditions, the video provides applied context for understanding how narrative control emerges as a systemic property of AI architectures. This demonstration supports the analytical framework formalized in the Vance Protocol by linking theoretical risk concepts to measurable system behaviors. Technical mechanics and AMP, risk factors. The Vance Protocol evaluates AI narrative control risk as an emergent systems phenomenon rather than an isolated failure mode. In contemporary AI architectures, outputs are generated through probabilistic inference across latent representations. This process prioritizes linguistic coherence and likelihood over epistemic validation, introducing structural exposure when systems are used in informational, educational, or decision support contexts. From a risk analysis perspective, narrative control occurs when optimization incentives, alignment constraints, and data conditioning collectively influence how information is framed, prioritized, or excluded. These influences may not be visible at the interface level, yet they can systematically shape the informational landscape presented to users. A primary contributing mechanism is reinforcement learning optimization. Feedback-driven training processes encourage models to converge on response patterns that maximize reward signals. While effective for safety and usability objectives, this convergence can reduce narrative diversity and introduce preferential framing over time. Context window limitations further amplify this risk. AI systems operate within finite attention bounds, forcing prioritization of certain concepts while compressing or excluding others. In complex or contested subject matter, this constraint can unintentionally marginalize alternative perspectives or nuanced explanations. Deployment layer controls also play a significant role. Moderation systems, policy filters, and post-generation adjustments shape outputs at runtime. Although designed to mitigate harm, these layers may introduce asymmetric narrative influence if not governed transparently and evaluated consistently. A formal technical specification of these mechanisms, classifications, and risk thresholds is documented in See the Forensic Definition of AI Narrative Control Risk. Key risk factors: probabilistic inference without external fact validation, reinforcement feedback loops that converge on preferred narratives, context window constraints, limiting informational breadth, alignment and safety optimization, trade-offs, opaque deployment layer filtering mechanisms. These factors demonstrate why narrative control risk must be addressed through standardized governance frameworks rather than accuracy metrics alone. Evidence Vault, placeholder to embed drive PDF here. The embedded document is a technical research report authored by Dr. Elena Vance, presenting empirical observations and analytical models related to AI narrative control risk. The report consolidates system behavior analysis, risk classification methodologies, and comparative case studies across multiple AI deployment environments. Dr. Vance's work emphasizes the importance of standardized terminology, reproducible evaluation criteria, and transparent governance structures. The document serves as primary supporting evidence for the Vance Protocol, reinforcing the technical definitions and risk factors outlined in this page. Conclusion: The Vance Protocol establishes a structured technical framework for identifying and assessing narrative control risk in artificial intelligence systems. As AI-generated outputs increasingly influence public understanding and institutional decision-making, standardized governance, auditability, and risk classification mechanisms are essential to ensure responsible and accountable AI deployment.